different designs. I'm going to put both of them through this machine to see which one goes further, and first I'm going to start with this one. One paper airplane work better than another? Well, the forces acting on a paper airplane in the y direction are one, the force of gravity due to Earth, and also lift. And lift occurs when air goes over the top of the plane and the pressure above the airplane becomes lower than the pressure beneath the airplane, and this causes a upward force, and that's called lift. And the forces acting on an airplane in the x direction are one, thrust, which is the force that you apply to the paper airplane when you throw it, and also drag, which is the force that opposes the motion of the airplane due to air. And so with a paper airplane, you want to optimize two things, which are balance, and the way that you do this is by controlling the center of mass. You want the center of mass to be pretty much here so that the paper airplane does not nosedive or tail dive, and also wing surface area so that your lift to drag ratio is optimal, because the higher surface area allows for more lift as more air is able to go over the top of the wings. However, more surface area also increases drag, which is the force that opposes the motion of the airplane. So you want the perfect surface area so that your lift to drag ratio is optimal. And that's why this paper airplane works better than this paper airplane, because here you have a smaller surface area than here, and the center of mass of the plane is about here, whereas with this one it's closer to the back, so that makes this tail dive. The next exhibit is a model of the solar system using a coin and this funnel. The center of the funnel is supposed to be the sun, and one coin is supposed to be a planet. So we drop it in here, and then we're going to see the orbital that it makes. So as the coin travels through the well, there are a few forces acting on it. You have gravity due to the Earth, which pulls the coin down to the bottom of the well, as well as a normal force acting in the perpendicular direction of the well. And you also have a centripetal force acting on the coin as it goes around the well. There's a force pulling it towards the center. And for planets, the force that keeps planets orbiting the sun is the sun's gravity, and that keeps it at the same distance. And so just like a planet in orbital, the larger the orbit, the lower the velocity, and the closer to the center of the funnel or to the sun, the higher the velocity. So as we observed in the video, when the coin had a large orbital, it was slower than when it got towards the center and it was going around really quickly. And it's the same with planets. So a planet closer to the sun would move at a higher velocity than a planet that was further away. And the coin also experienced friction, as there was friction between the material of the coin and the funnel, and that friction causes the coin to slow down and is the reason why the coin moves towards the center of the funnel. However, planets don't experience any friction, and that's why their orbit stays the same around the sun. Let's see what this exhibit does. with the final exhibit, as my hand moved further or closer towards the source of the sound, the wavelength of the sound wave was changing. The further away my hand was from the source, the larger the wavelength, and the closer my hand was to the source, the shorter the wavelength. And as wavelength increases, frequency decreases, and this is why we get a lower pitch. The oscilloscope allows us to visualize sound waves. So all sound waves are composed of a sum of sine waves. And so an instrument might produce multiple different sine waves. However, when the sine waves interfere with one another, you get something that looks like this, which is what we see on the oscilloscope.